Good day, everybody. This is a short video dealing with the atmospheric sciences and the chemistry of the ozone layer. This is to help people understand the second homework, which deals with the ozone and the ozone skeptics. This is for the class of Religion and Stateability, presented at Countryside Community Church in October and November 2016. So the learning objectives today is to learn about the ozone and how different refrigerants affect the ozone. This is a schematic of the Earth's atmosphere from ground level at the bottom here to space up at the top. You can see the immediate level that we all live in is the troposphere. This goes about 5 or so miles up into space. All of the mountains and everything else related to land is in this area. The stratosphere is the level at the top of that. It goes from about 15 to 35 kilometers, or about 7 to 20 miles. This is the level where the ozone is located at. Then you have the mesosphere and the thermosphere and the exosphere, which is pretty much outer space. And you can tell the altitudes here based on the kilometers on the vertical scale. In the late 1960s, early 1970s, Earth atmospheric scientists were measuring increasing levels of chlorofluorocarbons, or CFCs, in all levels of the atmosphere, particularly the stratosphere and even the thermosphere. The rate of concentration increase was increasing 3 to 10-fold depending on the measurement. And the rapid increase alarmed a lot of scientists, since there's no known sink for these chlorofluorocarbons in the atmosphere, particularly the stratosphere and the thermosphere. The only potential for it to go is to react with the ozone, which is in the stratosphere. The consequences of that concerned scientists, and they were wondering what would happen if these levels of chlorofluorocarbons kept increasing as rapidly as it was in the early 1970s. This led to a landmark paper by Roland and Milana from the University of California at Irvine in 1974, where they first published data showing that these human-generated chlorofluorocarbons were rapidly increasing, and by the year 2050 would grow to 30 to 50%, would grow to decay the ozone layer by 30 to 50%. At the time, nobody really knew how this would affect the Earth's atmosphere, but scientists generally agreed upon that this would be a bad thing. Many studies after that followed up and confirmed their conclusions. And in fact, most of the studies found that the rate of decay of the ozone was actually even quicker. So this rapid degeneration of the ozone layer led political forces to come up with the 1988 Montreal Protocol, which called for the phase-out of the CFCs, chlorofluorocarbons, by the year 2010. CFCs are man-made chemicals that are highly used as refrigerants and as aerosols. So CFCs were in most refrigerants, particularly car refrigerants. So as the growth of the automobile grew globally in the 1960s and 70s, a lot of those cars had air conditioners, and a lot of those air conditioners needed a refrigerant, and CFCs were used as refrigerants, and those would leak out of the car and into the atmosphere. Likewise, any type of aerosol can, like a WD-40, was also rapidly growing, and all those aerosols had CFC in it, and every time you squirted some WD-40 on something, that released a small amount of CFCs into the atmosphere, and added all together, that was a significantly large increase. NASA actually has a kind of a cool website where you can actually go and get satellite images that are same day or the same week, and you can actually watch the ozone hole as it changes over time. So the chemistry, and I'm simplifying this greatly, kind of looks like this. The ozone is 3 oxygen molecules bond together. And CFCs, or chlorofluorocarbons, are a man-made chemical that's a carbon at the base, has a fluorine and 3 chloride atoms. As this would rise up in the atmosphere to the stratosphere, there would be a lot more UV light accessible from the sun. And this powerful UV light would break the bond between carbon and chlorine. And since you had potentially three free-floating chlorine atoms for every CFC molecule, that chlorine would then react with oxygen either in the atmosphere or reacts with ozone and would break one of these oxygen bonds and bind with chloride. So chlorine is very reactive with oxygen. That would break down the ozone, or O3, to O2 plus O1, which would eventually could be breaking down to 3 O's, which is a very reactive chemical species. And this would also cause a degradation of the ozone. So that's what led to their banning. Scientists went back to the laboratory and said, okay, we can't have chloride. They come up with the next generation refrigerant, and that's called HCFCs, which is hydrochlorofluorocarbons. Hard to say 3 times. And so it's very similar. All they did was replace 2 of the chlorines with 3 hydrogen atoms to stabilize the molecule. Now, the bad news, it still had 1 chlorine. The good news, it only has 1 instead of 3 chlorines. So it greatly diminished the ability of this chemical HCFC to cause ozone depletion, but it didn't eliminate. Because it still has this 1 chloride as HCFC, or hydrochlorofluorocarbons, rose in the atmosphere, it got to the stratosphere, you still have the same problem. UV light would break this bond. You would have floating chloride radicals that would bond with oxygen and still cause degradation of the ozone, just at a much slower rate than the CFCs. So a lot of HCFCs have been produced, particularly after the phase out of the CFCs in 2010. And so most refrigerants today are HCFCs, and these are very common in most residential and commercial air conditioning systems. The other side effect is HCFCs are a much more potential greenhouse gas. So it still has 1 chlorine. Now it's causing greenhouse gases and global atmospheric warming potential. So now what do? So the scientists went to get back to the lab, and now they came up with HFCs, okay, which is simple hydrofluorocarbons. So what they did was just get rid of the chlorine altogether. And this is an example of an HFC. This is HFC 134A. This is a very common refrigerant in residential air conditioning systems, window air conditioning units, and some smaller commercial grade air conditioning units. So they got rid of the chlorine, so there's no longer any worry about ozone depletion, but all these hydrogens and now 2 carbons can increase global warming potential. And here's a quick table comparing the ozone depletion potential, which is on a scale of 0 to 1, with the global warming potential, which we'll get into a little bit later. So the CFCs first came out, again, they were greater than 1/2, and it had a very high global warming potential. Since the Montreal Protocol in 1988, CFCs were banned. Everybody went to HCFCs. Very much smaller ozone depletion potential. Most of these are under 0.1, with a decent but high rates of global warming potential. Since the ozone depletion potential is still there, because you still have that 1 chloride atom, they then went to HCFs, which are hydrogen fluorocarbons, which had 0 chlorine, so basically 0 ozone depletion potential. However, their global warming potential now greatly increased. So now what the market is doing, and some of the revisions to the Montreal Protocol, which has been revised 8 times over the years, calls for, it doesn't mandatory call for the phase out of the HCFs, but they are supporting a voluntary switch out from HCFs to low global warming potential HCFs. Same basic product chemical, they've just added some more atoms to decrease the global warming potential. Unfortunately, these refrigerants are not as effective. So the market has been slow to adapt because it's not as a good refrigerant, at least not yet. Until better products hit the market, most people are still staying with the HCFCs or the HCS, which has the high global warming potential. Here is carbon dioxide, again, 0 ozone depletion, 1 global warming potential, and an HCF R22, kind of very standard, typical commercial refrigerant. Again, almost no effect on the ozone, but has a high global warming potential. So this is a plot of the production of the 3 different types of refrigerants: CFLs, first generation, HCFCs, second generation, and HFCs is the 3rd generation from 1950 through 2010. So you can see here, particularly with the growth of the automobile, large increased production of HCFs, then that kind of continued to go up. We realized the effects of CFCs on the ozone. They started becoming banned, decreased to where it is now illegal to produce or even use CFCs. And then HCFCs could, here in the 1990s, when these results came in as being negative, now their growth started to boom, and they've kind of gradually gone up. And then in the early 1990s, they got rid of chloride altogether and switched over to HCFs, and now that increase has been growing. This is the same plot as before, but now going forward to 2015, but instead of production of refrigerants, this horizontal axis is now your carbon dioxide equivalent, or would be your global warming potential. So here we're at 2010, when CFCs were banned, HCFs kind of started picking up, and as you switch, and now these are called to be phased out by 2030, and so now everybody's going to switch over to these FCFs, but they have a large global warming potential and a long half-life in the atmosphere. So hence the increase in global warming potential. So as we phase out of these, probably in the next 20 years, and go to low global warming HCFs, again, they're going to stay down here with minimal atmospheric effect. However, these refrigerants to date aren't very good, so the transition and acceptance of these new chemicals on the market has been slow. So in 2015, the 27th Montreal Protocol meeting, that's when they voted to come up with a new amendment to the Montreal Protocol banning HCFs in favor of low global warming potential HCFs. That has not been written yet and hasn't not been accepted. Language stating the phase out of HCFs is included in the Kyoto Protocol dealing with global warming, and we'll talk more about that later. So hopefully that can explain a little bit of the chemistry and the reagents involved with the ozone depletion. For the paper you all have to read, I want you on Sunday, we're going to talk about 2 basic questions here. The Montreal Protocol was widely accepted and hailed by many countries across the country, across the globe, and for the most part, all the countries have agreed to it and kept with it. So the question I want you to think about is, why can't we duplicate this model with climate change and water management or food management or any of these other issues that we've talked about? The second question is, why excuse me, why has religion, particularly Christianity, seemed to always fight these scientific discoveries that led to improvements or warnings to our environments. Again, you've seen this play out time and time again from the early scientists in the Middle Ages, even through today, the changes in the tobacco industry, climate changes, ozone depletion, use of sugar, all these things. Christianity has not been on the forefront of this. So I want you to start thinking about why that is and what maybe we can do to change it. Hope this helped. See you on Sunday.